Hello gals and guys, Mr. Ambrose here with a video on the proof of the derivative for the natural log of x, which in class today we saw was equal to 1 over x. And so to help with this actual proof, I just want to first revisit something that you guys saw in Algebra 2 and or pre-calculus. Actually, I'm sorry, just algebra 2, most likely. And that was the compound interest formula, which is this formula here, which is used to determine how much money a bank account has after a certain amount of time and a certain amount of compound interest. Um, while you work with this formula, hopefully you saw that as the number of compounding periods goes off to infinity, this expression of 1 plus 1 over n raised to the nth power, as n is going to infinity, that all this just approaches e. And because of that, then you had this continuous compounding formula for PERT, but I claim that this particular idea right here is going to play a key role in proving what the derivative is for the natural log function. So with that being said, let's actually now formulate and set up the derivative using the definition of derivative to help us find out and prove that the derivative natural log of x is indeed just 1 over x. So for that, again, going to need 2 points. One point will just be x comma natural log of x, and the second point, as we've done all along with the definition of derivative, I'll go h units away from x, and then the y value to that point, given that our function is natural log of x, the y value would be natural log of x plus h. And to now derive the natural log function, right, setting up or using the definition of derivative, we'll have the limit as h approaches 0, and then we'll do this change in y values all over the change in x values, which ends up just being h. And as we've done all along so far this year, right, I'll try to do some algebraically to simplify down this expression. And in particular, what I will do here is use a property of logarithms that you guys learned last year that does come up occasionally here and there within calculus. And that is that if you have, or we have the difference of two logarithms, we learn that we can condense them into the single logarithm of the quotient of the two arguments of those respective logarithms. So I'll do that same, or apply that same rule right over here, and we'll get that this numerator will become the natural log of x plus h all over just h. And that's still all over h. I'm sorry, there's a natural log of x plus h all over x, and then that's all over just h. All right. And so now we have the single logarithm in the numerator, and I claim that we could perhaps simplify that down even further to make our life easier, and we'll have the natural log of just 1 plus h over x all over h. And for purposes of trying to make things just a little bit simpler, instead of having to deal with this h over x and then this other h over here, I'm going to do another substitution in here to just make our lives just a little bit easier. And the substitution I'm going to make is that I'm going to let the variable v be equal to that h over x. And so because of that, and because I have an h over here as well, if I use this particular equation, solving for h over here, if we multiply both sides by x, we would have that v times x would equal h. So making the substitutions of h over x is equal to this v, that v right over there. And then in the denominator where we have h is equal to v times x, so I'll make that substitution there. And then the other substitution you have to make here is, here we have that h is approaching 0, but now having made these substitutions, there's no longer any h in my expression. So I need to perhaps adjust what the variable that we're going to use here and what it's approaching. And because of this equation right here, I claim that because of this here, right, as h is approaching 0, if we, again, we're looking at this equation here, if h just approaches 0, x is remaining constant, then I claim that this whole fraction over here, so long as x is not equal to 0, this whole this whole expression over here, as h approaches 0, will approach 0, which means that v would also have to be approaching 0 for the equality to hold true. And so I'm going to substitute in v approaches 0 into this limit expression so that everything still is maintained and true and everything is still equal here. So now, okay, I've simplified things down a little bit, and we have here this quotient. And as we did earlier in the year when I had a limit of a quotient, I'm going to just go off to the side here, and I'm going to consider the limit of my numerator and my denominator as v is approaching 0. And if we look at this here, the limit of our numerator as v approaches 0, hopefully you would agree that just evaluating this limit, we would end up with the natural log of 1, and the natural log of 1 is equal to 0. So the numerator is approaching 0, and I think we would agree that as v approaches 0, the denominator is also going to approach 0. So we still have an indeterminate form of this limit, and we have to try to do some more simplification, some more algebra here to try to figure out what this limit will equal. And I'm going to continue this on the next page. So again, we have here the limit as v is approaching 0, and we have natural log of 1 plus v all over v times x. And so the algebraic simplification that I'm going to do here to kind of manipulate things is that we are dividing this natural log by v over x. But dividing by this v over x, I claim is the same as just multiplying by its reciprocal, which would just be 1 over v times x. And so doing that algebraic manipulation, we now have this here. And if we look at, we have this limit of this product of this expression times this expression. And so as v is approaching 0, I hope we'd agree that this part of our product here is still going to approach, again, as v approaches 0, that this would still approach natural log of 1, which is 0. But this other expression would end up being 1 over 0. So 1 over 0 as an answer to a limit, if we recall from earlier in the year, this basically means that this is either going to positive infinity or negative infinity. And so this particular limit, upon this evaluation at this point in time, what we have here essentially is that we have that the limit is equal in something that is an infinity times 0. And so I claim that this is another one of our indeterminate forms for limits. And we can't determine, basically that means we can't determine what the limit is just based on this here. Although part of this is going to infinity and the other part is approaching 0, we can't conclude that this is going to go to 0 or that this is going to go to infinity. We have to analyze this further, and that means more algebra is necessary. So knowing where this is going and just applying rules of algebra, this fraction here, I claim we can split this up as a fraction, two fractions that are 1 over x times 1 over v, and we'll still have this natural log of 1 plus v still being multiplied to all this here, and then applying properties of limits that we learned again from the beginning of the year, right? We learned that when we have a limit of a product of terms, right, we can split that up into the limit of one expression times the limit of our other expression and evaluate each of these limits separately. And so, okay, the limit of this first expression, because there is no v in here, I hope that we would agree that because there's no v in here, that as v approaches 0, 1 over x is just going to stay put. And so, right, this limit here, I hope that we would agree that this should just be equal to 1 over x. But the problem's now going to be, unfortunately, with this other limit that more analysis is going to be required here, because we still have technically this here, which is, as v approaches 0, is 1 over 0, which is some form of infinity, times the natural log of 1 plus v, which is, as v approaches 0, is still going to be 0. And so using another rule of limits, right, this here, I'm sorry, another rule of logarithms that you guys learned, right, and I'll actually go over here, sorry. This rule of logarithms says that if you had a constant being in front of your logarithm, we can take that constant, or that expression in front, I should say, of the logarithm, and move that up as a power of the argument of that given logarithm. And so that's what I'm going to do here. This 1 over v, which is being multiplied to the natural log, I'm going to move that up to be the exponent of the argument of this natural log, which the argument is 1 plus v, and now I have that raised to this 1 over v, which was originally in front of this logarithm. And now, okay, once again, try to consider, since I've done some more algebra here, if I try to consider perhaps what the value of this limit is here, that's going to be a bit complicated. And so what I'm going to do is, using another property of limits, is that the natural log function we know is continuous throughout its domain. And so for this here, because this is a positive 1 in the argument, this is always going to be positive values. I'm going to perhaps pull the natural log out in front of my limit, and then just focus in on the original argument of that natural log to try to evaluate what this limit is. But upon inspection of this particular limit, as v is approaching 0, I hope that we would agree that this base is going to approach 1, but this exponent, look at that again, it's 1 over 0, and 1 over 0 is some form of infinity, and so we have here something of 1 raised to, something that's approaching, I should say, 1 raised to the infinity. And so because we're approaching 1 raised to it, something that is approaching infinity, I claim that this too is another one of our indeterminate forms for limits. Because while we know that 1 raised to any numerical exponent is equal to 1, this space is approaching 1. And so because of that, you're going to see that this here, it may be 1, it may actually be some other number, and we have to analyze this further. And so that's what we'll continue to do here. So now to try to analyze just this limit as v is approaching 0 of 1 plus v all raised to the 1 over v, I claim that we already know what the value of this limit is. And so through a little bit of shenanigans and trickery and whatnot, I'm going to do another substitution here where I'm going to let u equal to 1 over v. And as a direct result of this, technically that means that, yeah, u times v is equal to 1, which means that v is equal to 1 over u. And so this particular limit here, making the substitutions, v again is going to be 1 over u, and 1 over v is equal to u. And then I have to be careful here. I have to now, because v is no longer here, I have to get rid of this v, but I claim that I can't write that u is approaching 0, because if we look at this equality right here, right, as v is approaching 0, right, over here, we know that technically that means that u, if we examine what u is going to approach, because it's equality, well, that means that u is going to approach infinity. And so because of that, with this limit, I'm going to now have to write the limit as u approaches infinity of this expression. But as I said from the get-go with that compound interest formula that you guys work with, and from that, I claim that this here is exactly what we had over there. That this expression, as u is approaching infinity, right, you learn from Algebra 2 that this approaches that very special number of e. And so that's the value of this limit here. And then now we can complete the evaluation of this whole kit and caboodle limit right here. And so going back to that, we had, and I'll do this on the next page, right? We had the limit of, this was v approaches 0 of 1 over x times the limit of v approaching 0, the natural log of 1 plus 1 over v raised, I'm sorry, it wasn't that, it was actually 1 plus v raised to the 1 over v. That's what we had right over here before I started to examine what this limit was specifically. And again, we said that this limit here is just equal to 1 over x because x stays put as v approaches 0. And then this whole thing here, right, we can pull the natural log out in front. And we have the limit of this expression here. But as I showed you over here, this limit ends up just equaling e. So we end up here, again, this whole thing is going to equal e. And then the natural log of e, you guys learned, or you hopefully remember, that is just equal to 1. And then, right, this here then concludes the proof that the derivative of our natural log function is just equal to 1 over x. And so I hope that you guys enjoyed this particular video and the nuances of all the mathematics that I showed you here, especially things that you guys have learned throughout the year, especially like, right, your different properties of limits, right, the limit of a product equals the product of limits, the limit of a continuous function, we can pull out that continuous function and then just look at the inner, the limit of a composition of functions where the outer function is continuous throughout, right? We can pull that outer function out and we can look at the limit of the inner function, right? Those are things that we learned earlier this year that were applied in this particular video. And the other thing I'll highlight is that there are these other indeterminate forms out there of limits, and usually you only have to deal with the indeterminate form of 0 over 0, or a little bit later on you'll see an indeterminate form of infinity over infinity. Those are the ones that you usually have to work with, but there are plenty of other indeterminate forms out there of limits, and so it's nice to be aware of all those things. So again, I hope that you enjoyed this video, and I hope that you all have a wonderful night. Take care, everyone.